Alright, today we're going to talk about different forms of energy. And when we're finished talking about different forms of energy and using a simulation, you're going to be able to complete your Part 2 of Law of the Conservation of Energy paper. Alright, so let's go back real quick and talk about the two different main forms of energy that we're going to talk about today, which are potential and kinetic energy. Alright, potential energy, you already know this, is energy that an object has because of its position or shape. And today we're specifically going to talk about its position. Alright, so something has potential energy when it has the potential to do something. And with potential energy, we're usually talking about the potential to move. Alright, so think about something that is high up has the potential to fall because of gravity. Alright, and then the higher it is, the more potential it will have because of the fact that gravity, the higher up something is, the more likely it is going to fall and gain kinetic energy. Alright, so what is kinetic energy? Kinetic energy is energy that something has because it is in motion, like this race car here. When something is moving, it has kinetic energy. When it's still, it does not have kinetic energy. Alright, it could have potential energy depending on where it's located, but if it's still, no kinetic energy, but if it's moving, kinetic energy. Okay. Alright, when we talk about potential and kinetic energy, we often talk about roller coasters because they take advantage of potential and kinetic energy to give you a fun ride. Alright, so like on this roller coaster here, it's going to start off by pulling the cars straight up to the top of this hill right here. Okay, and then it'll stop and it'll wait a second before it goes, and that's partly to give you a thrilling ride, but also up here at the top when it stops before it takes off down this hill, what does it have, potential or kinetic energy? Well, it's really high up, so it has potential energy. So the car will be released, and all that potential energy as it's going down the hill, it'll go faster, 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 and all that potential energy gets turned into kinetic energy because at the bottom of this hill right here is where it'll be going the fastest. Okay, so then it'll have kinetic energy and no potential because it'll be back down here at the bottom. But that kinetic energy will carry it back up this loop, and when it gets to the top of the loop, again, it will have mostly more potential energy. And then as it goes back down again, it'll speed up and it'll have kinetic energy. And then as it goes back up a hill, some of that kinetic energy will be turned into potential energy, and then gravity will pull it back down the other side and turn the potential into kinetic. So it's just constantly turning between potential and kinetic. And if you've ever ridden a roller coaster, you know that unless it stops at the bottom and gets pulled up a hill, there's nothing making it move other than potential and kinetic energy. And there's no motors making it go. The only motors are the ones that pull it up to the top of the first hill. Okay. Alright, in order to complete this paper, you're going to need to look at a simulation. So go to the link that's provided to you, and we were going to go to this energy skate park simulation. Alright. So in order to complete your paper, you're going to need to, once you get to this link, once you follow the link and you get here, you're going to need to click on the intro. Alright, it's going to give you this little simulation. And your skater here, what you're going to end up doing is putting your skater on this little half pipe and let the skater go back and forth. Okay. And what is this telling us right now? Well, when you started the skater up at the top, she had potential energy, right? Because gravity could pull her down. And then when you let her go, some of her potential is getting turned into kinetic energy and then back to potential again. Alright? But we can let the simulation help us out. Alright, so go ahead. If you've done this already, you're going to go ahead and pause it and reset it. So what I want you to do when you're doing this is turn on your bar graph, and you can even turn on the grid so you can kind of compare where she is, and turn on the speedometer, and this will tell you how much speed she has. Alright, so once you've got those on, if you put her at the top, you'll notice before you go that over here on this bar graph that her potential energy is up. There's no kinetic energy at all. And the potential is equal to the total. All right, so let's let her go and see what happens. Notice how her speed goes up. She's going fastest when she's at the very bottom. Okay, so if she's going fast, does that mean she's got a lot of kinetic energy or a lot of potential energy? Well, since kinetic energy is the energy of motion, the faster she's going, the more kinetic energy she's going to have. And since she's going uphill, she's going to slow down and actually stop. When she gets to the top of the hill and her speed is 0, you can notice over here that her potential energy goes way up. So let's watch the graph, okay? Potential's up when she's at the top of each side. Potential's way up. And when she's at the bottom, what's up? Well, she's got the kinetic energy way up because she's going fast. Why does her potential go down when she's at the bottom? Well, gravity is no longer pulling her down anymore because she's already at the ground. So that's why her potential is going down to 0, but her kinetic is way up because she's going fast. Notice how the total never changes. Okay, that's part of the law of conservation of energy, which means you can change energy's form, but you can never create or destroy energy. So the amount of energy she has is constantly all the way to the top here. All right. So if you need to complete your paper, okay, look where you need to stop her. You're going to need to pause her at the top of this hill on the left and down at the bottom, and you're going to need to pause her about halfway up on the side. Okay, so let's go back. So let's pause her at the top. Okay, so now when she's at the top here, you can copy this graph onto your paper. Okay, so she's at the top of a hill. She's got all potential energy, no kinetic energy. All right. All right, so let's put her back up at the top and then see if we can pause her at the very bottom so we can do spot 2 on your graph. Okay, so I'm going to hit play. Actually, I'm going to pause her right there, and you can use this little button to step her forward, kind of like a one step at a time. All right, now she's at the bottom. All right, and if you notice now, her kinetic energy is all the way up, and that's equal to her total. Her speed is up pretty high. So let's copy this down to your point 2 on your paper. All right. And then once you get that one copied, let's hit play again and let her go. And this time we need to stop her about halfway up the right-hand side. So we'll do about right. Oh, it's a little too far. So we could step her until we get her where we want her to be. So I'm going to click my forward button. Actually, I'm going to hit play again and pause and see if we can get her about right halfway in the middle. It's pretty close. Let's try it again. So we want her right about halfway, about right there. Oops. Didn't do it again. Alright. Let's try one more time and stop her about right there. Oh, that's pretty good. You know what? We can switch it over to slow motion. So it'll be easier to stop her where we want her. And we want her about right there. Perfect. Okay. So now she's halfway up and halfway down one side. And I want you to copy the graph. The kinetic and the potential are about equal because she is equal distance between the top and the bottom. So her kinetic energy is going down and her potential energy is going up because she's going faster and faster and faster. So one thing that I notice students often get wrong is we ask them where do they have the most kinetic energy on like a roller coaster. They have the most kinetic energy at the very bottom, because that's where they're going the fastest, at the very bottom, because the gravity has been pulling them, accelerating them all the way till they get to the bottom. When they get to the very bottom, and we can, unpause it and watch, when she's at the bottom is when her speed is the highest. Okay? All right. So now what I want you to do is, after you've got all those graphs copied on your paper, I need you to come back over here and answer these questions. And you can look at your graph and you can look at your simulation to answer it. What type of energy does the skater have at location 1? Okay, so when the skater was up here, look at your graph. What kind of energy does she have and why? Why does she have that kind of energy? Same thing for location 2 and location 3. What type of energy does the skater have at location 2 and why? And for question 3, what kind of energy does the skater have at location 3 and why? Sometimes the skater might have more than one kind of energy. So you need to make sure you answer the why part. Okay? If you don't answer the why part, you're not doing this right. All right, so once you finish answering the questions on there, then you can go back and you can play with your simulation some more. You can change it to different types of ramps and watch the potential and kinetic energy as she does these different things. You can also click on here and you can add friction. Okay, what do you think friction's going to do? Well, friction creates, I don't know, you tell me. See what happens. All right. And also notice, if you're playing with this one without the friction, does she ever stop? And why do you think so? All right. So play with those different ramps and different graphs. And then once you're completely done, you can click on the playground and you can build your own ramps. Okay. But I need to see that you're finished with your paper before you start going to the playground part and playing around with it. So if I see you playing around and not finished with your paper, we're going to have a problem.